Now, let's try to look at the concept of martingale, which is a stochastic process where we can say the current value of that particular process, the today's price or the today's value, is an optimal estimator wherever, whatever is the process we are talking of, wherein the current value is an optimal estimator for the future value. That kind of a stochastic process means the current return, example, the current stock price return, if it is a better estimate, if it is the best possible estimate for the return for the next period, we call those kind of processes as martingale, which in other terms they are also called as those kind of processes where there is no drift. And what we typically see is there are huge number of applications in the world of finance which use the concept of martingale. The whole theoretical structures behind the pricing and hedging of the derivatives is purely based on this concept of martingales itself. So it's very important for us to understand this fundamental behind the martingale. So we are looking at it more from the perspective of a conditional expectation. All we are looking at is, though we have some kind of a process where we have a conditionality on large number of periods before, if it is a martingale, this entire thing will translate into the value at a point. See, if I'm talking about for y n plus 1, it is as good as the expected value of yn itself. This is where we are looking at it as a martingale. That too, in a discrete time, we are getting the values at y1, y2, y3, so on, y at different points in time, though I know the values of y. And if I want to estimate the value of this particular process at time period n plus 1, it is purely dependent on the current value, which is yn. This is what we apply in discrete time. Whereas in the continuous time, because we can't talk about y1, y2, we are not doing it in that particular form. So what we say is yn plus 1 conditional on the filtration up to, let's say, time period n. Then we are simply saying this could be equal to the expected value of yn itself, or the current value that is present at time n itself. So that is where the martingale presentation typically changes in the continuous form, right? So whatever we are talking about the expectation for the next period, we are simply looking at it independent of the previous, right? Even if I know all the previous information, it hardly matters. So I'm simply looking at it as the expected value of any yn given ft. It is as good as the y the it is as good as yt itself. This is what is a typical martingale scenario in case of continuous. So instead of taking the different conditional expectations here, the whole conditionality has been packaged into the filtration, which is nothing but the history of the values known up to the previous of all the previous periods up to that particular period. And in case of a discrete, we also need to know that the expected value of the modulus of xn should be less than infinite, and the same thing should go even in case of a continuous case also. One more important rule. So the expected value of yn plus 1 will be based on yn. Similarly, in case of continuous, all these individual conditionalities will be represented by the filtration up to that particular point in time. So based on this, you could very clearly say that whatever is the current value xn is, if it is a martingale, this is the better expectation, this is the better value for this particular process. This is the better estimator for the value of this process at time n plus 1, right? And whenever we are seeing the discounted price of a financial asset, when we are using a particular probability distribution, that is following the risk neutral mechanism. Even in that case, we see a kind of a martingale approach itself, right? So it's as good as looking at for all the processes, any conditionality of the previous periods, it's only the current value becomes a better estimator for the previous. So a simple thing we'll take a simple example. Let's say I'm talking about a simple process e power lambda bt minus half lambda square t. This is a process that I have, and I want to check out with if the filtration is available up to time period t. The information is available up to time period t for a standard Brownian motion of bt. Now I want to see that this is a martingale, xt is a martingale. So which means all I have to show is expected value of xt given fs should be equal to xs. If I am able to show this, this is fine. So let's try it out. Expected value of e power lambda bt minus half lambda squared t given fs. Now bt, we'll write it in our usual notation, e to the power of lambda bs plus bt minus bs, right? Lambda bt minus half lambda square t given fs. Okay, so now let's expand it. Expected value of e power lambda bs plus lambda times bt minus bs minus half lambda square t given fs. Now we'll take out all the constant terms. This is a constant. Bs, because we are conditioning on fs, bs is not a random variable. We know the value of the process at time s. So this becomes expected value. I can take out e power lambda bs outside, saying it's a constant. Even this is a constant, minus half lambda squared t. It's only bt which is a variable. T is not a variable. T is a time period which is fixed. So all I know is here e to the power of lambda bt minus bs given fs. Now I know bt minus bs has independent increments and stationary increments. So which means it is not dependent on fs at all. So directly this is becoming e to the power of expected value of e to the power of bt minus bs. Now we know that bt minus bs is a normal distribution with mean 0, variance t minus s. Right? It's a standard normal. It's a normal distribution with mean 0 and variance t minus s. So it's as good as, if you look at this expression, it is e power lambda x. And if you remember, this e power lambda x is typically talking about is a moment generating function, if we are talking about e power lambda x, where x is a normal distribution with mean 0 and variance something, it's nothing but it's a moment generating function of a normal distribution. If I am having expected value of e power lambda x, it's a moment generating function, and this value, the value of this moment generating function, we know that it is equal to e power mu lambda plus half sigma square lambda square. So I'll substitute that now. The value of this entire thing, which is a moment generating function of a normal distribution, instead of x, I'll take it, for this kind of a form where x follows a normal distribution, I can take the value of it as e power mu lambda plus half lambda squared sigma squared. Now mu is 0, sigma squared is t minus s. Mu is 0, sigma squared is t minus s here, and this is what I'm going to reflect here. So the value of this entire function is going to become e to the power of mu is 0, so the first part does not exist, half lambda squared, sigma squared for me is t minus s. So this part becomes e power half lambda squared t minus half lambda squared s. And this entire thing is multiplied by this constant which has been taken out. So it becomes lambda bs minus half lambda squared t. I take this out. This is becoming e to the power of lambda bs minus half lambda squared s, which is exactly same as xs. So we can very well say that xt, which is of the form e power lambda bt minus half lambda squared t, is a typical Martingale going with the filtration, especially with respect to period t. The same logic, probably we'll take one more example to make things clear for us. So let's say I want to try out bt squared minus t. I want to check out whether this is a martingale with respect to filtration T, with respect to the filtration Ft associated with Bt. Now I know that this is Xt. Let's try it out now. Now all I want to show is the expected value of Xt given Fs should be equal to Xs. In that case, it becomes a martingale. So I'll try out expected value of bt squared minus t given fs. We'll write it as expected value of bt, we'll write it as bs plus bt minus bs whole squared minus t given fs. So this is coming out as expected value of bs squared plus bt minus bs whole squared plus twice bs times bt minus bs minus t given fs. Now out of this, I can take out the constants part to start with. So because we are doing it with respect to s, bs part is nowhere a random variable for us now. We can very well take out the bs part. So I'll simply take out this part bs squared, taking it as a constant, and I'll take it as 2bs, which is a constant, times the expected value of bt minus bs given fs, right, for this part. Now for this part, expected value of bt minus bs whole squared given fs, and because t is a constant, I'll take it as t. And now we know that bt minus bs is following independent increments. So applying that, probably the first part bs squared remains the same. Right now, this given fs is completely removed because only bt minus bs is completely independent with respect to the past values. So I'll remove that given fs kind of a factor. Right, so this becomes expected value of bt minus bs whole squared minus t. And now we know that bt minus bs is a normal distribution with a mean 0, variance t minus s. So obviously the first part, this is bs squared, fair enough. The expected value of this is 0, so this entire term is becoming 0. And expected value of x squared, right? We know that variance is expected value of x squared minus expected value of x whole squared. Now I know expected value of x is 0. So variance is coming out same as expected value of x squared. So expected value of this is nothing but the variance. Variance is t minus s minus t. So this is becoming bs squared minus s, which is nothing but xs. So if at all I am able to prove that this is the expected value for the future conditioning on a particular filtration is going to be the current value itself, then we can very well support our concept of being a martingale. So this is one important concept that we need to be comfortable with. A basic concept of martingales and Brownian motion used in various aspects of financial calculations and financial pricing and modeling. So a comfort level is very much expected in these different areas. All right.